Welcome to the first section of our exploration into the unsung heroes of electronics. The world of electronics relies on a constant flow of electricity. But, the electricity that powers our homes and devices comes in two forms: alternating current, or AC, and direct current, or DC. AC, which is delivered by power outlets, constantly changes its direction, flowing back and forth like a wave. DC, on the other hand, flows steadily in one direction, much like a river. Many electronic devices require DC to function correctly. This is where rectifiers come in. Rectifiers are electronic components that convert AC to DC. They act like one-way valves, allowing current to flow in only one direction. This process is crucial for powering a vast array of electronic devices, from smartphones and laptops to televisions and refrigerators. Without rectifiers, many of the technologies we rely on would simply not work. Moving to the second section, let's delve into diodes, the building blocks of rectification. Diodes are two-terminal electronic components that serve as the foundation for rectification. A diode's ability to conduct current in one direction while blocking it in the other makes it a critical component in rectifier circuits. Imagine a one-way street for electrons. That's essentially what a diode does. A diode is made from semiconductor materials, typically silicon or germanium. These materials have unique electrical properties that allow them to control the flow of current. When a positive voltage is applied to the anode, or positive terminal, of a diode and a negative voltage to the cathode, or negative terminal, the diode allows current to flow. This is called forward bias. However, if the voltage is reversed, with a negative voltage applied to the anode and a positive voltage to the cathode, the diode blocks the flow of current. This is known as reverse bias. This directional control of current is the key to how diodes enable rectification. By selectively allowing and blocking current flow based on the direction of the voltage, diodes form the basis of rectifier circuits. Different configurations of diodes allow for various types of rectification, each with its own advantages and applications. Now, in section 3, let's talk about the half-wave rectifier. A simple start. A half-wave rectifier is the simplest type of rectifier circuit. It utilizes a single diode to convert AC to pulsating DC. This circuit allows only half of the AC waveform to pass through, effectively chopping off the negative half cycles. The result is a pulsating DC output that is not smooth, but still unidirectional. Imagine a wave crashing on a shore, but only the crests reach the beach, while the troughs are blocked. This is analogous to how a half-wave rectifier works. The positive half cycles of the AC waveform are allowed to pass through the diode, while the negative half cycles are blocked. This simple design makes half-wave rectifiers easy to construct and inexpensive. However, they are relatively inefficient as they utilize only half of the available AC power. Finally, in section 4, let's explore the full-wave rectifier, doubling the efficiency. A full-wave rectifier addresses the efficiency limitations of the half-wave rectifier by utilizing both halves of the AC waveform. This type of rectifier employs two diodes arranged in a specific configuration that allows the full AC waveform to be converted to DC. Unlike the half-wave rectifier, which discards half of the AC power, the full-wave rectifier captures both positive and negative cycles, resulting in a more efficient conversion process. The circuit arrangement of a full-wave rectifier ensures that regardless of the direction of the AC current, one of the diodes will always be forward biased, allowing current to flow through to the output. This effectively flips the negative half cycles of the AC waveform, resulting in a pulsating DC output that utilizes the full AC input. The output of a full-wave rectifier, while still pulsating, has a higher average voltage than the output of a half-wave rectifier. This is because it utilizes both halves of the AC waveform, resulting in a more consistent flow of power. Full-wave rectifiers are more efficient than half-wave rectifiers and are commonly used in applications where a more consistent DC output is required. They are often found in power supplies for electronic devices, battery chargers, and other applications where efficient AC to DC conversion is essential. Section 5. Bridge rectifier, the king of conversion. The bridge rectifier is a widely used type of full-wave rectifier that offers several advantages over the traditional two-diode full-wave rectifier. It employs 4 diodes arranged in a bridge configuration, which eliminates the need for a center-tap transformer, simplifying the circuit design and reducing costs. The bridge configuration of the 4 diodes ensures that regardless of the polarity of the AC input, 2 diodes will always be forward biased, allowing current to flow through to the output in the same direction. This results in a full-wave rectification process, effectively converting both positive and negative half cycles of the AC waveform to DC. The bridge rectifier offers improved efficiency over the 2-diode full-wave rectifier as it eliminates losses associated with the center-tapped transformer. It also provides a higher output voltage as it utilizes the full voltage across the AC input. Due to its efficiency, simplicity, and cost-effectiveness, the bridge rectifier is the most popular choice for AC to DC conversion in a wide range of electronic devices. From small power adapters to large industrial power supplies, the bridge rectifier plays a critical role in powering our modern world.